Hello everybody, my name is Morris and welcome to my presentation for Physics Lab 4. So as a quick introduction to this lab, we are looking at the motion of an object attached to a spring traveling in a circular motion. And so we were using Newton's second law and the momentum principle to model or to update the position of the mass on the spring according to the momentum principle based on the two forces that were acting on it, being the spring force as well as the force of gravity. Additionally, we are also using the energy principle to help model the motion of the mass on the spring. And we're using different types of energy, specifically kinetic energy, gravitational potential energy, and spring potential energy to model the motion. The system in this case would be the spring, the mass, and the earth, and the surroundings would be everything else in the universe, pretty much. And so these are the formulas that we use to calculate each of those respective energies. So here is the spring potential energy, with K being the spring constant and S being the difference in between the length and the relaxed length. And then here is the gravitational potential energy formula that we use, and here is also the kinetic energy formula that we ended up using. So here's my video and tracker. The axes were set with the origin at the fixed point of the spring, and the 0.7 meter calibration stick was set at the length in which just the mass hanging dead on the spring. And so, using that information and from tracking it in Tracker, we were able to come up with a computational model using this code in GlowScript. So here we can have the spring mass that was given, which is 0.402 kilograms. Here was the calculated spring constant and relaxed length of the spring. This was based on the period of oscillation found in Tracker, which ended up being about 1.519. And then using the formula that was given in those edX videos, we were able to calculate the spring constant as well as the relaxed length. And so here we're actually calculating the different energy values at the initial point of the mass on the spring. And then here in the while loop is where we start looking at the updating and using different principles. So here is where we're using the momentum principle as well as Newton's second law to update the position of it based on the two forces that were acting on it. And then additionally here we're able to see the energy principle at work as we're looking at the changes in energy here. So we keep the initial kinetic energy and look at the change as well as the gravitational potential energy and the spring potential energy as well as the total energy. And so when we run this program in GlowScript, we get this result. So the blue ball is the model that we're looking at, and the red ball is the observed motion. And so these are the graphs that are produced. And so if we look at these graphs that we get from GlowScript, we can see that our model was actually a pretty good approximation of the observed motion. So when we're looking at the y position versus time, here we can see that it was pretty close. There's some minor deviations like here and here, but that's mainly due to the fact, probably due to the fact that the video and the tracker, weren't quite synced up. So possibly some human error with the tracker dots, as well as the poor video quality. Again, blue is the predicted and red being the observed. And then here's the x position versus time. And again, it's pretty similar, a slightly more deviation, but again, it was a good approximation. Again, here, the blue is the predicted, while the red is the observed values. And then here is the change in energy graph. So blue is the change in kinetic energy, red is the change in gravitational potential energy, and green is the change in spring potential energy. And then this orange line over here is a change in total energy. And so if we look at whether or not the energy principle was satisfied, we can say yes. So looking at the system that we defined earlier, the system should have no work done on it by the surroundings, as well as no heat transferred to it from the surroundings. So the change in energy should end up being 0 for the entire system throughout the entire time. And as you can see, it stays around at 0 throughout the entire time. So that would coincide with our energy principle. And as you can see, the oscillations of the different other energies make up for that fact. And then another question that we might ask is which form of the period is best for estimating the oscillation. So if we use it based on the x position, we'd get a period value of 1.646 seconds. And if we use it on the y position, we get a period value of 1.519 seconds. And so when I compared these two values in GlowScript, the 1.519 value was actually significantly better at predicting the motion of the mass on the spring. And this is likely due to the fact that this is more closely associated with the actual back and forth movement of the spring compressing and extending, as opposed to the x position oscillation, which is more about the pendulum-like motion as the object is swinging back and forth. So this would probably be a more accurate representation if we're looking just at the spring. Thank you for watching.